Good evening, everyone. I'm coming from the University of Almeria. This is the talk that I am having right now. I have to say, before to start, that two weeks ago, I was attending a course in visual thinking. What is visual thinking all about? Keep things simple. No. So what is adjusting or fitting kinetic parameters? Then you need the data, you need the model, you need the tools. So pretty obvious, right? So let's take about the data. You need the data because it's the evidence that supports your model. And also you have or need some tools to do the fitting or the comparison. What about the colors? You should have hope in your data, illusion for your model, and confidence for your tools. And there is also a second meaning. What is hope? In Spanish is also the word for expectation. So when you look at the data, you have to be, they are getting like they should be. Also, for model, you have ideas. So you need to think with different perspectives, and then you get some more quality models. And finally, confidence means also computers hands-on. So now I'll take a bit or every of this piece. So I'll start with data. What you have here is the main philosophy for quality improvement. So you have overall variation equals process variation plus measuring system variation. So the first thing that you have to do when you get or collect your data is to do assessment of your measurement system. You can say, well, I have enough measuring, I have no error, so this is not possible, no one can trust you. You have more error than variability in your process, then you are a fool. You are wasting money and wasting time. What you have in there? Oh, this is a guy asking, what about me? What about me means the reproducibility. In terms also of system measurement, you have to consider the equipment error plus the personal people working. I think this is a good place just to draw some proposal, because you have a lot of students here, and then you exchange from lab to lab. And maybe I don't like paperwork, I don't like either bureaucracy, but maybe you can think in validate your methods, like following a rating procedure maybe once a year, twice a year, with different people that change or go to your lab. And this is also a thing that you may have improvement in your results. Okay, how data looks like? Well, on the right, from, I don't know what is your background, but from any one of you that has a course in, let's say, kinetics, you see concentration over time, constant, decreasing, and more decreasing. So this is the zero-order model, first-order model, second-order model. Well, this is all obviously with no error, and this is what you really get. Can you directly, just by eye, tell what is the right one? So this is what is adjusting kinetic right now. So you need to get what is the right curve. And I also want to say something more about data, which is classification. We work with per compound, which is fine to do kinetics. We also have the transformation product. There is enough room there. We don't know. And we also have a lot of kinetics doing with all the DOC, COD that I think should be remains. For transformation product, we always have the same question. Okay, you have removed your parent compound, so you get no toxicity. Well, you don't know. Because you remove your parent compound, but you have the same DOC. So it's not the initial toxic one, but you have something. So you have to consider what is the final target of what is the final objective of where you're treating the water. And I also have to say here that we should change the way that we record our data and use and add, let's call metadata. That is everything that is related or done with only the, let's say, concentration profile. This is the real data. But you also has to include pH, data of the collection, water metrics thing, everything of that. And what is this for? What this is for? Maybe do some other kind of model, other perspective of the model, which is what we are entering now, which is machine learning. But this is a subject of another talk. Okay. Let's move to the model. What are we talking about? We're talking about chemical reaction. And now I want you all to visualize what is going on when you say there is a reaction, right? Or yeah, there is a reaction going on. What you see? We need some agreement. Because you can see what is going on. Is that you have the electronic cloud is moving, collapsing, what? You are getting some changing in the energy level, and what about the wavelength thing? So, what is the model? We need a real agreement. So, in reality, this is very difficult to have, so maybe you get this. This is the model for an underground student, right? What is a collection? No reaction, whatever. And this is what you get when you are a PhD student. So which of the two is the correct one? None. Right? What is the definition of the model? Well, all models are wrong by definition, by default. Some are useful. And that's it. Okay. So what is our agreement? Our agreement are mass balance. So we do accounting. And accounting is the model for everything. From accounting, you can have, let's say, a mechanism for the reaction. This is the proposed mechanism. This is the accounting that by now you should have a very clear distinction between what is the mass balance and what is the kinetic expression reaction rate. So you need where you collect your data, if you are in a batch reactor or in continuous reactor, and reaction rate expression. And I have to say, reaction rate, you always need to measure experimentally whatever the system you are getting. And especially if you want to do a scale. So the other thing about the mechanism is that you can get there just doing some data approximation, like some, I'm not explaining here, but you can go there. Well, and if you have, let's say, reminds or a course on kinetics, let's do a toy example, very basic. You have here data on time and concentration, get the reaction rate, and we apply the most famous let's say, procedure to do adjusting kinetic, which is linearization plus ordinary least square. And what is that? You plug the data on Excel, for example, right-click on the line, and then you get it. You're done. You've done your parameters. And you have the slope, that is almost 1, so the reaction is first order. And from the ordinate, you can calculate the kinetic constant. You can do the same thing, let's say, with MATLAB. In this case, you have to know, let's say, the syntax. Use, for example, polyfit. Then you get the same answer, of course. And also, because it's not it's a direct procedure, you can apply just directly the computation, like, for example, for getting the slope and then for getting the ordinate. And even, whoa. Okay. And even you can use another thing, let's say Minitab, and then, of course, you get the same answer, plus a very nice picture, a very nice analysis of variance. So that means you have to test what is the error in your parameters. Okay, now let's move to the nonlinear thing that is the more general thing. So in the case of linear square, we do direct computation. In the case of nonlinear, we need optimization. And what is optimization? That is a procedure. Then you start in a value and get the solution, let's call, for a certain exactitude, which is your tolerance. So in this slide, you can cast every search method for optimization. All are iterative. You need a starting point. You move that point, choosing, let's say, one direction, and then you compute what is your step in that direction, and then you update the equation, and you're done. Well, this is the algorithm, and this is like in the map, how do you get there? Let's say this is your optimum solution. This is where you start at the beginning, and you should end there. From another point, let's say you are at the same distance from the final answer. Maybe from this path, it takes 20 operations, or even more, only 2. And maybe you start from another one, and you have also to change some of the method that you are working on. So, which is the guarantee that you get from the only optimum? Well, multi-star plus meta-heuristics. But for now, we only use, let's say, the classical method. Well, in my case, I use MATLAB to do this thing. This is a very nice book to start with. This is Applied Optimization with MATLAB Programming. So as you see, I am the computer guy. And you also have, if you want all the, let's say, slang for optimization, then you can go into GAMS, which is General Algebraic Modeling System. If some of you that are like Python or something like that, this is the last model in computing, then you can do Julia, which is also from that page. And of course, if you are a MATLAB user, you have the MATLAB Central that gets you almost all solutions. Well, and also you have mathematics and everything. I have here this example taken from the page, and you see you have a very simple reaction, and we want to do a parameter estimation. So the first thing is reaction kinetics. That you see, you have two differential equations. Then you need to define what is the objective function, which is the sum of square error. Also in there, you have to know what is the syntax in every of the platform that you want to work in. Well, in the case, this is the solution from the page. This is the solution from MATLAB. It's the same. And I put in there because I want to point you, like, for describing your system, you are using two equations. And here, for describing my system, I use 4 equations. Because this is full order model, and the other one is the simplified model. But you get the same result. So what I'm telling here is that from the point of view of the expression, then you can do different things and get to the same solution. Okay, I think I'm going very fast, and probably I will end maybe 10 minutes before. As I said, this is the 10 minutes. Okay. Oh. This is the MATLAB graphical user interface that you can also, where you control the parameters of the method that you are applying. And in here you have what is your algorithm, the stopping criteria you did know, and also you have what is the computation of the Axiom metrics. I assume that you all know what is the Axiom metrics. Am I wrong?
I don't know what it is.
No? It's the matrix of second derivatives of your function. What? Oh. And then this is one of the techniques that you use when you are computing the SEM. Let's say, when you want to compute the search direction, which is where are you moving to look for the optimum, then you can do or use the information how the function is changing, which is called the gradient. This is very, I think you all know this. But you also can compute the second order or second derivative. Use this information to get different search direction. I mean, you can use this computation. That means your method works quickly, but you maybe also get some problem because the computation can get you into some numerical problems. Well, this is the summary of the things that you need to do when you are doing the parameter estimation. So the first thing is you solve your dynamics. So I recommend always to get only a piece of code where you put all the equation, get your parameters in, that means the kinetic constant, and run the code and see if you get something that is workable. This is also a nested loop. Then this is the inner loop. When you compute this, then you get a profile of your concentration. With your profile of concentration, this is only simulation. Then you need to compute, let's say, merit function. What is a merit function? the difference between your actual real data between your simulated data, your error. And also you can weight this computation by some factor that maybe you get some nice future to get to the solution. And once you have there, what is the output of this thing? It's only one number, which is the criteria what you're using to say this combination is better than this one. So you need, let's say, a number, and then you get, in the final answer, you will have a zero, a solution. And finally, you put this output into this third thing, or another piece of code, and this is where you have all the solvers in MATLAB or in other program. What are these module chain doing? These are changing your kinetics in here. And so, chain kinetics, another difference, and again, say if you are less than your final, let's say, tolerance. So this is how it's working. It's iterative, and that's it. So you need to separate the three pieces to identify possible problems. You can have problem here, problem there, and in most cases, this is the easiest part where the problem is solved right away. Well, these are the sample. Nonlinear parameter estimation via, well, where fmincon is a MATLAB function, a built-in one. Okay. This is the scheme that you are doing when you are doing the parameter estimation. So in the first thing, you have to separate the quantity of your data. You use some of the data to do identification, which is actually get the unknown parameters. And once you end there, you have your model solved. And then you use another piece of data to check if you have the comparison. Well, I skipped this. This is the syntax for the function. And in MATLAB, you can do the same thing with another, let's say, option that is also the function for nonlinear fitting. In this case, there is only two loops. So this is the main one, where you change your parameters. And this is where you get the dynamics part plus the error computation. And the difference between the two methods is in this last one, your objective function is always difference between data and your model square. In the other one, you can have another one. So this is an example of how it's working. You have your data, you compare your observed data with your prediction. This is the parameter of the model. In this case, this is the Y0 condition and the kinetic constant. This is only a very simple first-order model. And also, from using this method, you can also have directly the interval of confidence interval of your parameters. And once you're done, okay, and at the end you have to do if your model was right, then you do the comparison of the residual. So the residual, what is the difference between your observer, your model, and your your data and your model. And you should get a picture when you have average 0, something that your variability is constant. And this is the two main things that, well, there are more things, but these two are the main ones. This is another sample for the same thing. In this case, the model was a little more with more profiles, but you also get a very nice fitting, and you are doing 4 parameters. And finally, we apply this method. In one case, this is the top removal, where we use a higher level or hydrogen peroxide. You have the equation here. And here, for example, this is my objective function. You see there is no square. So you can use a function that has to that accumulate the error and don't cancel positive and negative. And also you have to identify what is your data for getting the parameters, and what are your data to get the validation. And finally, this is the last work, also done in the fitting. In this case, you get the value here, and then you also have the computation of a standard deviation. And to get there, you run, let's say, bootstrap method or run Monte Carlo method that I'm not explaining right now because we are out of time. So this is my final picture. So I put there because I like. I hope this is it takes half an hour or maybe 1 hour to forget 50% of what you hear. It takes 2 days to forget the whole thing. But if you have a picture, then maybe you stay longer. So if you remember the colors of my first slide, then you get the picture. Thank you very much.